we are going to start on page 52 or 62. 52 of week 13 slides. He starts us off with an example. So this is, again, slide 13 of, slide 52 of week 13. We're starting off with a question. We've got a function, y is equal to x squared minus 3x minus 4. And just for the sake of completion, let's go ahead and factor this out before we do anything else. Yeah? Looking at this, you factor this as x minus 4, the quantity times x plus 1. Agreed? So what this tells us then, looking at the graph, is that this thing is going to have a 0, a root, at x equal to 4, that's going to be over here. And at x equal to -1, it's going to be over here. Okay. Okay. So our graph of this thing, it's going to look something like this. Now, what the question's asking us is to find the area bounded by our function and the x-axis. So it's asking us to find the area bounded by this thing and I don't want to use that, I want to use the other. And the line y equal to 0, right? So that would be this area down here. Now we know that the area between two functions can be written as the integral from a to b of f of x minus g of x integrated with respect to x, where f of x is greater than or equal to g of x in the interval a to b, right? Agreed? So looking at this thing, what would play the role of f? Based on our setup here, what would play the role of f? Would just be the constant function 0, right? So here, we're going to say f of x is equal to 0, and g of x is equal to x squared minus 3x minus 4. So our integral is going to be 0 minus x squared minus 3x minus 4 dx. Now we have to find our bounds. Well, our bounds are going to be from a to b, a being this point here. So this is -4. and this point here. My mistake, -1 and 4. So we're integrating from -1 to 4. Well, hey, we can rewrite all of this, right? This 0 is really doing nothing for us, and we can distribute this negative all the way through. So we're going to get the integral from -1 to 4 of -x squared plus 3x plus 4 integrated with respect to x. And from here, we're just going to do the normal process, right? Nothing crazy is going to happen from this point on. Just to make sure you can see all the way down. Yep, cool. I can see what they see on the other tablet. But jumping to the next slide, just to kind of reiterate this whole process, we've got our function here. We know it's going to have a 0 at -1 and at 4. And we know we're finding the area bounded between it and the x-axis. Since anything above the x-axis is unbounded, right? You go from y equal to 0 up to y equal to infinity, then the bounded region must be what's below. So that is everything here. And looking at the calculations now, we go about doing the same thing. We say, hey, let's factor this out, find our a and b. Now let's set up our integration. Since 0 is always above or equal to our function from -1 to 4, then our function gets set up this way. Reducing everything, simplifying, and then doing the calculations from that point on, right? So nothing crazy is going to happen from that point where we got it to on. So, what about something like this now? This changes a lot, actually. This function is rather crazy looking. Or this area, rather. So first, let's try to even graph these things. First thing to notice with this cubic, we factor out an x, right? So this cubic is going to have to go through the origin. Right? Also, because the leading term is positive, we know that it's going to have to look something like this, right? This far end is going to have to go up. This far end is going to have to go down. So that tells us it's going to look something like this. Now, our second function, g of x, It also has to go through the origin because we can factor out another x. X squared plus 2x is equal to x times negative x plus 2. Our leading term is negative, so we know that this has to be facing down, right? We also know we have to go through the origin and through x equal to 2, right? I just so happen to know that when we graph this, we're going to have an intersection here. And this needs to be over more too. So the graph's not perfect yet. I'm not going to be able to get it perfect. So I'm going to go ahead and draw, or just skip to the next slide. This is actually a really hard set of graphs to draw by hand, just because of the way they intersect. But from this point on, we need to find out what this intersection point is, right? So we've got two of them that just so happens to occur this way. So what we're going to do from this point on, set our functions equal to each other. So back one, we're going to set 3x squared minus x squared minus 10x equal to negative x squared plus 2x this is going to tell us that subtracting everything from each side, right? We're going to get 4. My mistake, it's not 4x squared. We're going to get 3 x cubed plus 0 minus 12x, right? So here, you're going to be able to factor out the 3x to get what's left inside is x squared minus 4. It's going to be equal to 3x, x plus 2, x minus 2, right? Once we factor it all out, okay, so this is how I knew we had an intercept here. So I went ahead and did this in my head and was able to see this particular intercept had to be shared. So the first thing you notice just from setting up our equations and factoring out that x was they both had to go through the origin. Now, by setting the two functions equal to each other and solving, we found that this intercept had to be a shared point. This is x equal to 2. This value is x equal to negative 2. And of course, we have the origin. Now, why is this important? This is important because if you notice, what we're trying to find is this area here. region, f of x is greater. But in this region, g of x is what's dominating. So we have to break up our integration into two parts. That's what this is telling us. Does that make sense? Folks at home, does that make sense?
Yeah.
Yeah.
Awesome. So since we have to break up our integration into two different parts, what we're going to do is we're going to say, all right, this first part is the integral from x equal to -2 to 0 of f of x minus g of x dx plus the second part, which is going to be from 0 to 2 of g of x minus f of x dx. So what is this doing? This is saying this part is our first set of area. This part is our second set of area. This is our first area. This is our second area. So all we're doing now is saying, all right, break this integral up into two parts. Our function's on top here, f of x is on top, and then here g of x is on top. So because this area is area 2, and it's associated with g of x being the largest, and this is area 1, associated with f of x being the largest, you can break our integral of like this. So from here, we're just going to do everything like you normally would. We're going to have the integral from -2 to 0 of 3x cubed minus x squared minus 10x minus negative x squared plus 2x dx plus the integral from 0 to 2 of -2 minus 6x squared plus 2x minus 3x cubed minus x squared minus 10x dx. Now we're going to simplify these as much as we can, right? It's going to be the integral from -2 to 0 of 3x cubed. This x squared and this x squared is going to cancel. And what we're going to be left with is this -12x dx, right? Because this cancel that. Now coming over here, we're subtracting this -x squared. So these are going to cancel again. What we're going to be left with is the integral from 0 to 2 of 2x minus 3x squared, or 3x cubed, plus 10x, which we can of course rewrite as 12x minus 3x cubed. Now I want to make a point here. We had a rule before about integrations that we could swap the bounds if we wanted to. I'm not going to do that because it's going to be confusing for right now. So from here, at this point, we just do the integrations like we normally would, right? So we set up the integrals, we simplified them as much as we could, and now we're just going to integrate and apply our bounds and do the arithmetic without point on. Cool. So really, there's nothing too terribly new here. It's just going to take some time to stop, think your way through this problem, right? Based on the situation that you're given, what do you need to do step for step for step to get out all of the information to set up these integrals and solve? Having said that, we have a new idea of consumer surplus and producer surplus. The idea of consumer surplus and producer surplus is saying, all right, given a demand function and a supply function, we have some point of equilibrium. We're going to label that x naught p naught. Now we're going to say, take the line y equal to p naught. It's just going to be a constant line, right? Find the area below it, bounded by the supply function. That's going to tell you the producer surplus. Take and find the area above it, bounded by the demand function. That's going to give you the consumer surplus. Make sense? Does this make sense to everybody as far as like just definitions are concerned? Yep, cool. So let's say we're given a demand and a supply function. First thing we need to do is set these things equal and find out what that x and that p is, right? So we're told our demand function, I'll label this as b of x, is equal to negative 0.36x plus 9. And our supply function, I call that s of x. That thing is equal to 0.14x plus 2. Setting them equal and solving, we're going to find that p of x for s of x gives us negative 0.36 x plus 9 is equal to 0.14 x plus 2. Since this is negative, why don't we just go ahead and add it to both sides and subtract 2 from both sides. When we do that, we're going to get 7 is equal to 0.50x I don't know about y'all, but I seem to remember 0.5 as being equal to 1/2, so we can multiply both sides by 2 and get that x is equal to 14. now we're gonna have to put 14 in and find out what P is. We can put it into either function. I'm going to put it into the supply function. I'm going to say I still don't know what that value is, so I'm jumping to the next slide. Find out that it is 3.96. 3.96. Go. All right. Now, producer surplus is this area down here, right? The function bounded below or bounding the bottom of it is going to be the demand function, I mean the supply function, right? So this is going to come out to be 3.96 minus our supply function dx from 0. We're integrating up to 14 here, ready? 14. And this is going to give us our producer surplus. Now, to get our consumer surplus, we're integrating from 0 to 14 again, but now it's going to be d of x minus 3.96 dx. Why is that? Why are these two functions, why are these two integrals the way they are? People at home, can somebody explain it to me? Why is the producer surplus that particular integral? Well, the reason is these are supposed to be finding the area above or underneath this line bounded by either our demand or our surplus function, right? The producer surplus is bounded above by that straight line, but bounded below by our supply function, right? So that area then is going to be the area underneath the straight line minus the area under the supply function. Hence this integral. Similarly, consumer surplus is the area under the demand minus the area under that straight line. Make sense? And that's why we get these two integrals the way they are. Now from here, we would just go through, plug everything in, and solve the integration, just like we normally would. Yeah. I am skipping this problem and going straight into 656. Do we have time? Yeah, we got 18 minutes. All right, go. So before I get too deep into this, I want us to recall at the very beginning of all this stuff about the definite integral, I had said that this thing was like adding up of the area of a bunch of small triangles, right? And setting the width, rectangles. And setting the width of those rectangles to be really small, right? That's what we started off this whole section with, was just me saying this and saying, I'll come back to it. That's what we're going to do now. That said, this is slightly outside of the scope of the class in the book, but I'm going through it right now because the book presents it to you in a way that I think is more confusing than what it needs to be. If I explain some of this background, I think it'll help clear up and demystify some of what's happening. So, to start off with, we need some new notation. We've got this funny symbol. It is a sigma, capital sigma. Okay, what this means is you're going to take whatever this function is and keep replacing the I with values between A and B and add each of them up. You're going to start off at I is equal to A, and then you're going to keep changing them by integer values up till you get to B. Make sense? So to see an example of these, let's say we've got the sum from I equal to 0 to 5 of I. What this symbol means, what this notation is telling us is, I'm going to take 1, or in my mistake, 0, plus 1, plus 2, plus 3, plus 4, plus 5. You're going to add them all up. Now, I wrote this initially as a function, and that's because we can change what we're adding up. We can change this to be, say, like I got up here, I squared, or j squared rather in this case. This thing then becomes 2 squared plus 3 squared plus 4 squared plus 5 squared. So all we're doing is we're saying, all right, take j, square it. Well, j at first is going to be 2. Now go to the next integer value, or whole number value. That's 3, square it. Add that to the next one, and keep doing this successively, right? Similarly, we could have something a little bit more intense. Have something like the sum of k equal to 3 up to, let's say, 5. I'm going to change this a little bit. K plus 3, this thing squared. This would come out to be 3 plus 3 squared plus 3, my mistake, 4 plus 3 squared plus 5 plus 3 squared. And now we can reduce all of this, right? You can say this first term is 6 squared plus 7 squared plus 8 squared. Oh, that's a happy coincidence. I didn't mean to make these two complete each other. But this is the idea of sigma notation. All it's really saying is, do this function, but start off by replacing I with A. Then do this function again with the next integer value and add that. Do that again with the next integer value, add that. Keep doing it over and over and over again. Make sense? So the reason why this is important is because what we're about to do is do iterative addition. And that's all this is. It's just iterative addition with some rules, right? What we're going to do is we're going to say, all right, let's take an area. Let's take a curve first. Let's define an A. Let's define a B. Now, from here, let's break up our interval from A to B into a couple different parts. In particular, we're going to generalize this to parts, n number of parts, of length B minus A divided by N. Makes sense? This is how we're going to generalize it in a minute. But for right now, we're just going to say, let's break this up into 3 parts. So we've got N is equal to 3. Now, with these 3 interval chunks, let's make rectangles. We can make them in a couple of different ways. You can make a rectangle setting the far right side equal to our function, the far left side equal to our function, or any value in that interval equal to our function, right? And we'll say that's the height of our function. Normally, we would start off introducing this idea by saying, let's set the left side. Let's do that again. Let's do that again. So what we've got now are these rectangles here. Which kind of approximates the area under our curve. Does that make sense what I mean? Kind of, sort of. But notice we've got some errors in here, right? This chunk is too much, this chunk is too little, and this chunk is too little. So if we take and divide this by 4 parts now, we get a little bit less error, a little bit less. So what we're doing is we're saying the area under our function from A to B is going to be equal to, rather it's going to approximate the area of each of these rectangles added together. And that's what we're seeing in this example here. Is we're saying the area from A to B underneath our function is approximately equal to the sum of the area of each of these rectangles, or the sum of the area of each of these rectangles. Now notice this area is smaller because we're consistently underestimating, right? This area is larger. So we're overestimating and underestimating, right? Now, what this is called is the Riemann sum. What we're going to do, we're going to say, let's take our x-axis from A to B, chop it up into a bunch of parts, n parts. Those parts are going to have a length of B minus A divided by N. So this is going to be B minus A divided by 3, B minus A divided by 3, B minus A divided by 3. This value here is going to be A plus delta X this value is going to be a plus 2 delta x. And this is going to be a plus 3 delta x. And we can check the math here to make sure that this is in fact equal to b. We're coming over here and saying, all right, we set n equal to 3. So 3 times delta x is going to be b minus a. So a plus 3 times delta x is going to be a plus b minus a, or just b, right? So far this is shaking out to look decent, right? Like it's getting us somewhere. Now we're going to say, pick a value somewhere inside of each of these intervals and find the height of your function. Find your function value. Set that equal to the height of the rectangle. The only thing is you have to use the same rule for every rectangle. So if you're going to use the left side of the rectangle, you got to do it for every rectangle. Do it for the middle, you got to do it for every rectangle, so forth and so on. Now, the area of each of these rectangles well, it's going to be equal to delta x times the height, right? Well, the height, let me write it a slightly different way, L times the height. The length is going to be delta x, and the height is going to be your function value at some point in that interval. And using traditional notation, we just call that x star. So the sum of all of these is going to come out looking like this. We're going to say, starting at 0, so we're iterating. There's a typo here. Should have been starting at 1. Starting at 1, we're going to break these up. Yeah, it should have been starting at 1, or this should have been k minus 1. Either case will work, and that's just because of the way the algebra shakes out. If we start at n equal to 1 and keep adding up till k, we've done k operations. But if we start at n equal to 0 and add up to k minus 1, we've done k operations. So this should have been, there is a typo in here. It should have been k n equal to 1 f of x star in delta x. Or equivalently, a minus 1 n equal to 0 f of x n star delta x. And really, this is just about how we want to label things. Either case works. So far, does this make sense, what we're doing? What this represents is the area of each rectangle. So this is saying, take the sum of the area of nth rectangle n equal to 1 up to k. That's all this is saying. And that makes sense based on what we've got written up here, right? Check it out. Delta x times f of x star is the area of a rectangle. we're saying the nth rectangle is exactly that, right? So this describes the area of the nth rectangle. Okay, now, new question pops up, and I am going to quickly minimize the slide and go to here. Just to show this idea. So a new question occurs. What happens when we let the number of these intervals go to zero, go to infinity? What happens when we let them grow? Does that make sense? What I'm asking? So to give us an idea of what's happening, notice the sum of their areas is going to get a lot closer to the sum or to the actual area under the curve, right? So taking more and more and more rectangles, we're going to get a better and better and better approximation. And so far, that's all we're doing. We're just approximating. Like, if we take more and more and more rectangles, that means these widths, well, they have to get smaller and smaller and smaller, right? What does that sound like to you? The limit, right? The limit as delta x goes to 0. What's the limit of delta x going to 0? Dx, right? So what this turns into then if I can get back to that slide, is going to be the definite integral. The limit as delta x goes to 0 becomes a definite integral from a to b. Now, new question comes up. Where the hell does a and b come from? How did that just suddenly show up there? Well, what's happening is we're saying take some value of x in the interval delta x plus some number of other times, right? So what I'm trying to say is, coming back to this down here, we're taking a value of x for the first rectangle between a plus delta x. For the second rectangle, it's going to be between a plus delta x and a plus 2 delta x. But if in the first rectangle, this width is going to 0, then the only x value you can choose from is a, right? And in this last rectangle, the only x value you're going to be able to choose from is b, right? And for every rectangle in between, it's going to be whatever that x value is. Excuse me, right? So this is the same thing as saying add up for each x value from a to b, your function of x times some infinitely small width. This gives you an area under the curve. So what the definite integral is really a limit of sums. Does this make sense? Yeah. Cool. Now, we are over time, so we will come back to this next class, but in the meantime, I will let you all go. If you all have any questions, I'll stick around.